Okay, now we're going to talk about set notation. So as we saw in the previous slide, we can write sets by enumerating all of its elements inside curly brackets. Sometimes using some tricks like here where there's a pattern that repeats, you don't have to write all of them. You can just, once the pattern is obvious, you can just use the 3 dots. So as we did in both the set of integers and the set of natural numbers. Now, let's see in which other ways you can denote sets. Okay, so let's use set notation. So first, let me give you another definition. So definition 2. So the objects in a set are called elements. Right, so for example, we have that, let's see, 3 is an element of the set. Let's do 1, 2, 3. Oops. Okay, so here we have a set with 3 elements. The set containing the numbers 1, 2, and 3. 3 is in there, so 3 is an element of the set. Now, if an object x is an element, so I'm using x as just a variable, it's just any object. If an object x is an element of a set, let's give it a name, a set S, then we write x is an element, kind of looks like this turn around E, right? So x is an element of S. Otherwise, if x is not in the set S, you write the same thing, but you do a line like that through the symbol. So a line going from right to left, or left to right if you're going up. Okay. So let's do just another quick example. And I'm not numbering these examples because they're very short. So just another example. Let's do 7 is an element of the set of integers, which we saw in the previous slide. Right, 7 is in there. But negative 7 is not an element of the set of natural numbers, right? Because the natural numbers is just the integers that are greater than or equal to 0. Negative 7 is negative, so it's not in this set. So that's how you use this notation here. Now, as I mentioned, it's not always possible to write down a set by listing out all of the elements inside brackets. Well, if the set is finite, you could do it, right? If it's not very long, like here, the set is finite, it has finitely many terms, so I just enumerate them. Also, you saw that it's possible to use this notation if there's a sort of repeating pattern. So for the set of integers and of natural numbers, there's this repeating pattern that we just increase or decrease the integer, right, by 1. So we can use this sort of shortcut where we use 3 dots, and that makes it obvious that what we're doing is just we're just following the pattern. Now, it's not always possible to do this because not all sets have patterns like this. So in order to deal with those situations, we're going to introduce this notation here. So just let me make a note of that. Note, not every set can be written by listing all of its elements. And even if a set is finite, you might not want to write down all of its elements, right? Because let's say you have a finite set, but the set has 1,000,000 elements. That's still finitely many, but you don't want to write 1,000,000 elements between brackets, right? It's going to take forever. All of its elements. Okay, so now I'm going to show you how we're going to write sets when it's not possible or it's not easy to write them by just putting brackets and enumerating each of the elements inside the brackets. Okay, so now let's actually start numbering our examples. Let's do example 1. So example 1. We want to write down the set of all even integers using set notation. So what is set notation? Set notation is either when you write your set like this, where you just write the brackets and enumerate each of the elements of the set, or with this other way that I'm going to show you right now. It's very easy to remember. So let me do it a couple of times. So we want to write down the set of all even integers using set notation. So we're going to do it like this. I'm going to open brackets again. We're going to write X here. And then I'm going to tell you what each of these symbols mean as you read them from left to right. So think of this first bracket as saying the set of all. So that's what that bracket is saying. So the set of all, this is saying just X, set of all X. I'm going to put a colon. That colon you want to read as such that. Okay. So we have a left bracket, left curly bracket. Read that as the set of all. X is treated as X, and then the colon read it as such that. Okay. So we have the set of all X such that, and then you just write the defining property of the set. Right. So what is this defining property or properties that the elements of this set have? Well, they're even integers, right? So they're integers. We know that we can write that X is an integer if we just write X is an element of this symbol, right? But it also has to be even. So we can just write and X is even. And then this, what you write after the semicolon, or the colon, sorry, is whatever defining properties that you have for the set. And then once you've written that, then you just close the curly bracket. So again, we wanted to write down the set of all even integers, identify what are those properties. Okay, the two properties is that they're integers and they're even. Okay, now use this notation. The leftmost curly bracket means the set of all. Then X, meaning that, okay, we're looking at the set of all objects X, such that, that's what the colon means, or that satisfied the properties that X is an element of the integers and X is even. Okay. Now that we've used this notation here, now we can actually write down how to write the set of the set of rational numbers. So let's do an example 2. So write down the set Q, or of rational numbers, using set notation. And again, we're going to use the same sort of notation that we use. We're going to start with the left curly bracket and then work from there. Okay. So let me write set of rational numbers equals. Okay. So again, this means the set of all. The set of all X such that and actually for rational numbers we need a little bit more. So we write the set of all X over Y such that. Right, so now there's two variables here. And again, this colon means such that. Okay, so we have the set of all X divided by Y such that. So what are the properties that make this a rational number? And if you haven't seen this definition before, then you don't know what it is. So let me just write it here. So it's a defining property of these objects of the form X divided by Y. Well, X and Y, so X are integers. So X is an element of the integers. y is an element of the integers. And since y is in the denominator, we don't want to divide by 0, so we say that y is not equal to 0. So in other words, what is a set of rational numbers? Is a set of all integers, or numbers of the form x over y, where both x and y are integers and y is not equal to 0. Now, that's the set of rational numbers. The set of real numbers is a little bit harder to write down, so we're going to do that a little bit later. So let me make a note of that. We need more information on, for this particular case, on operations on sets. So we can't write down, can't write down R using set notation yet.